about this thing that we call index. And the first thing to say about index is that the name that we use internally for it, meaning index, is not great in a database context because it naturally creates confusion for people coming from the traditional database world, because the first thing that they think is, oh, this is a database index, and surprise, is not. The reason why it's called index is historical and has to do with the evolution of the system and the original place it came from. And we have stuck with the name, at least from the point of view of how we talk about it internally. And sadly, it's not only internally because it actually shows in our API. So the data structure and the classes in Java are called index. And that's how it is right now. There have been talks about renaming it. In the last conversation that I had about potential renaming it, the reason we haven't done it is because we want to keep the possibility of easily moving code between Deephaven Enterprise and Deephaven Community. And index is one of those critical pieces of infrastructure that is subtle. We make changes there that have a lot of impact. If we make a mistake there, things become slow. If we make something slightly better there, if it's 2% better, it actually has a cascading effects and things can get a lot better sometimes. So it's difficult. Anyway, the best name for this thing really will be something like RowSet, because what it really represents, or the intention of this data structure, is to essentially be able to store the moral equivalent of query results. And with that, I'm going to start presenting. I'm going to use a slide from a little presentation that I prepared at the beginning of the year about some improvements about the index, but I'm going to use the first few slides from that to talk to you guys. So I'm in the process of clicking through getting to presentation, share. Hopefully now you see my screen. And click. You should see the presentation now, if somebody could confirm that's the case.
Yes.
Yep.
Cool, great. So I probably should say present here so that this looks better. I should go back. Sorry about that. Okay, cool. The name of the presentation is Index Memory Utilization because the improvements that we did around that time had to do with that, but it has an intro section explaining index, and I'm going to use that. You guys can find the whole presentation in the shared drive. I'm going to give a link at the end of the talk, okay? So a little bit about what this is and what this is not really relevant for now. This is the first slide of what I want to talk about. So imagine you have a table with some data on it, right? And let's say that you want to execute a query on the table, like some where clause that we have here on the right-hand side, right? So we have actually 3 columns, right? Sim, time, and price. And there is an implied column that doesn't really exist in the table, but is how we reference data. Let's say that we have this table stored on this. This is some historical table that has some, it's a Parquet file or something. We can refer to individual rows in the table by the offset of the row. So we can say that, for instance, this row here is at offset number 1, right? Sorry, I went back. So with that, essentially, when we want to execute a query in the engine, and the engine is going to calculate like a derived table, which is the results of that query, we get something like that. The idea being that essentially you can represent the answer as just the offset, and when you actually need to get to the data in the answer, you don't need to have a whole copy of the original table and the resulting rows. That way, essentially, you save on memory because you don't have to copy over rows that are part of a result from one table to another, right? So this idea, right, you can imagine that if you have a chain of operations one after another, if you do where, then join, then last by, it can create several intermediate results, which in turn create new indices that represent those intermediate tables, and then at some point an end result, right? That's one basic application of index inside the engine. Another one is when you do things that have grouping behavior. And in typical grouping behavior, essentially for a single row of the result, you need to reference multiple rows in the source table. So in this case, it's actually kind of worse from the point of view of memory utilization, because you end up with an index on, oh, sorry, again did that. You end up with an index on each one of the rows. So for a grouping result, you can have essentially the result row number 1 have a reference to 2 rows in the original table, right? And again, to try to paint an image, right? Imagine the web UI showing you the resulting table from a query that you just ran. You see some rows being painted in the web UI, right? The way the engine is getting the data to paint those rows is essentially going back to the source data for the original table via the index representation in the derived table. We do not have a copy of the actual data, right? That is not completely true, because there's a little bit of caching, but it's a good mental model to think about this. I'm just, letting you know that I'm lying a little bit, but it's a good mental model still. Okay, so what do we need to do, right? What is this data structure at the end of the day? Well, we need to represent sets of integers. That's it, right? At the end of the day, we need to say, oh, the results are rows 7, 25, 38, 39, and 40. That's it. It's a set of integers. So how complicated can this be, right? I mean, computer science 101, how can you represent a set of integers? A couple of ideas come to mind. One basic idea would be we can just have an array, put all the values in an array. The values happen to be ordered because the original set is ordered. So if we can take advantage of that, that will be good. Do we need to take advantage of something like that? Yeah, we do, because a basic operation or an index is to answer the question, do you have number 7 in the index, right? Is row number 7 from the original table present in the answer, right? To answer that question, if you have just values in a long array and the array has 1,000 elements, if you have to visit each element in the array and ask, is this 7? Yes, no. Is this 7? Yes, no. That's not very efficient. A better way will be to have the elements in the array in order, and then you can do something like binary search and end up with your answer in log n time instead of O n time. Another idea that comes to mind pretty quickly when you look at how results of queries come in practice is that basic question, right? How much memory do I need to represent 1 million values? So you think a little bit about that. It's like, well, I mean, 1 million integers. Let's say I'm using, these are long, so 8 bytes for integers. So 1 million 8 megabytes. Well, what if your answer happens to be all the table and you have a consecutive range? So essentially what you're representing is all the numbers between 0 and 999,999. There's a very compact way to say that. You just need 2 integers. You say the range between 0 and that value. So we need a way. So first requirement, right? We need to be able to store this efficiently. We don't want to use a lot of memory. Second requirement, we want to have a memory efficient representation for something that very commonly is going to have consecutive ranges as part of the values that you want to store. Something that I didn't say before, sorry. The requirements for the data structure essentially are you want to get quickly to the values, so we need to represent this in an efficient way, right? And when you create query operations, right? If you look at any kind of database book or articles, is when you look at database engines internals, you end up with a natural mapping between operations like join, where, etc., and set operations like union, intersection, and difference, like the mathematical notion of a set and the operations for the union of two sets, I want the result. The intersection of two sets, I want the result. So these are operations that you want to be able to do on an index, because when you execute a query, you're going to be doing the algorithm for implementing the query is going to be doing unions, intersection, differences, looking for individual values in the case of a join and things like that. And again, two requirements, right? Things have to have an efficient memory representation, because typically we're running things on one particular machine and we're limited by how much memory is in that machine. And also they need to be fast, because you want to see the query result today, not next year, right? As part of satisfying querying, when we execute persistent queries in the Deephaven enterprise side, and in general, right, we create lots of indices inside the engine. If you were to take profiling, if you run a profiler against a running worker, right, the actual engine process, right, the Java process, and look at memory utilization, you will see that at the top, very near to the top, typically right after any columns that have string values, if they have individual strings, you have the indices taking most of the memory of what that process is doing. So if we make a change in, like, the index representation now is 10% cheaper in terms of memory, that's a big impact in terms of the total memory that the worker uses. Another thing that happens is that we have the need to represent multiple types of indices. When we were talking about grouping and the fact that we have one index per row in that case, those indices are typically very small. They are just a couple of values. As a result of the grouping, they may be 10 rows, 20 rows, 5 rows, right? It's very different than an index that is the result of an operation over a table with, like, hundreds of millions of rows that is in turn, tens of millions or whatever, right? So we have a need for a data structure that is able to represent a few values very efficiently when there are ranges, many values when it's big. So this is not going to be simple, because to have too many requirements. So there's this line here, right? Fast, memory efficient, simple implementation. Pick two, the implementation is not simple. We don't have a lot of time today, so I'm not planning to go into the details of the implementation of the data structure that follow in this presentation in too much detail, or actually, likely in any detail. But I want to give you today is enough of the core ideas, so that if you have a need to go into that, you can, because you're prepared. And also, with the ideas, you are going to get enough of an understanding of how index behaves under the hood, so that when people talk about, the efficiency of an index in a particular query execution, you have some basic mental model that allows you to think about it and, make sense of what that conversation is. Okay. And of course, for anybody who has, like, more interest, if you guys look at the details later, I'm more than happy to answer any questions on Slack or one-to-one in a call or whatever you may prefer. So I think from the point of view of leaving enough time for answers, we have around 5 more minutes. So I'm going to go through this. A couple of core ideas on the implementation follow, okay? The first one is this. Many data structures for order data use a tree. You may have seen, binary search trees in college if you had a computer science background, or if you have used in a programming language data structure like a map, you have an idea of key value pairs being associated, and the typical representation of that is a parent node with pointers to a left and a right hand side, and then you have a way to search to the left or the right depending on some order and relationship, right? The problem with following pointers in memory is that modern machines are very fast when accessing memory that is in the same area, and when you jump around in memory, because of the cache. And when you ramp around in memory, that efficiency is lost. So the problems with data structures that are pointed intensive is that they cannot take advantage of cache locality, and you give up a lot of efficiency. So to the point that we can use contiguous memory locations, at the end of the day, represent data in some kind of array, that's going to be a lot faster than trying to follow and chasing pointers in memory. Okay, that's the first idea. The second idea is a little bit more complicated, and I have I'm going to use some pages from Wikipedia and some images from there to kind of like give an idea there. It's coming from the functional world. In the functional world, there is this idea called persistent data structures. The word persistent here is a little bit misleading because when people talk about persistence, they think about saving things in a hard drive. The word persistent here is used in a different way. Persistent essentially means that when you have a data structure and you do a mutation and you do a modification, for instance, you have a set with 3 elements, 1, 3, and 5, and you add another element to the set and you have a new result which has now 4 elements. That mutation creates a new data structure, and you are able to preserve both the original one and the result. Why is this important for us? Because we have base tables and then derived tables and chaining of multiple tables with inputs from other tables. So the indices that we create along the way have a lot of common parts. They typically share most of the elements from the previous index with some modifications along the way. So to the extent that we can save memory by having common parts of different indices for different tables point to shared parts for the values that are common to all of them, that helps us save memory. To understand that, I really need to show something, so I'm going to actually switch.
Can you also comment on when that ends up working out poorly?
So it actually goes back to the previous one, right? In the sense that a representation like that is going to require pointers, and that's going to hit the cache locality part. So we're going to end up with some combination of things that do use pointers and share pieces for the things that are being pointed to, right? And also you need to do this efficiently. You do need this notion of keeping track of which particular, not exactly which index is using which piece, but you need a way to essentially ensure that if somebody is using a common piece, let's say that I'm representing one part of the index as an array, right? This is a big data structure. I have some kind of tree. The trees are done in a way that we don't have individual elements in the base nodes, in the leaves. We actually have arrays with values, right? We have some way to organize that. We have one array for one particular piece of this index story. And when another index is created as a result, we just make a pointer to that array, right? Now, if the original index is modified and I have somebody else referring to this array, I want to be sure that I don't do the modification also for that other index that is not suffering that modification right now, right? So in order to be able to do that, I need to keep track of who is using this. And if somebody is using this, I need to use some kind of reference counting to know, oh, somebody else is reading this. If I want to modify it, I really need to make a copy. I'm probably getting into too low-level details for that answer. I don't know if I actually addressed what you were asking, Chip.
I was mainly asking for, so using these functional data structures, it makes sense in most cases because you're not copying things, but there may be some performance consequences of that this group may need to be aware of. And what would that look like, and where would we see those? Does that make sense?
Yeah, it totally makes sense. I'm trying to, think of an example of sorts, right? What comes to mind, I'm sorry, but I'm kind of like going back to what I was trying to say previously. I don't have something smarter to say in a sense, but I'm coming back to the notion that these data structures essentially do save memory, right? To the extent that you're smart about how you represent what is actually in the nodes of these things that do look like trees, right? But they do that by, you know what? No, I'm going to give an example. The example is going to be better. The example is actually going to answer your question. I'm pretty sure. So let's put a pin on that. Give me 1 second, okay? Share. I'm going to first talk about the basic idea, and then I'm going to go to the example that is going to explain that, okay? So you are hopefully seeing two list type data structures with X, S, and YX in the screen right now?
Yep.
Okay, cool. So let's say that you have two lists, okay? 0, 1, 2. Here, I'm borrowing from the Wikipedia page for persistent data structures, right here. Probably if I make my window smaller, you'll see the text in a bigger font. So these are two independent lists, right? And let's say that we want to do the concatenation of those two lists, right? Given this representation of a list as a data structure, we can do this trick. And this is the underlying trick, and that's it, right? This is the result. CS in Zulu, is the result of concatenating XS and YS. But you will notice from here, right, that we are actually not using any memory to represent CX, right, for the YS part. We actually had to copy all the nodes for XS. So we have these 3 nodes here as a copy, but we are sharing the part about YS because the actual YS list just is a pointer pointing to this node here. And the YS list itself can be represented in the same way, no matter it being part of the CS list for the second half. So this trick, this idea, right, can be actually extended to more complicated data structures like a tree. It's a little bit more complicated, and I think this is where the answer to Chip's question is going to come to play. Let's say that you have this tree, okay? This now is a tree. Let's say that you want to insert an element, this element here. The trick that we do is that we copy the branching from the root node towards the leaves, and we modify one node, which we need to also copy. This is not anymore the same node, and we add the element that we want. If you follow the pointer for YS, you notice that it's a structural sharing for this piece here, right? A, B, and C did not need to be copied, right? And in the example here, it does look like there is a lot of copying, right? Because we're copying 4 versus sharing 3. But with a little bit of imagination, you can probably see that if this tree is a lot bigger, meaning taller, you are going to have a lot more sharing happening. And essentially, we're going to be duplicating O log n, one branch, right? For the total n elements. So we're going to be keeping most of the elements, right? So here, I think, is where the answer to Chip's question lies, in the sense that this process of copying is essentially creating new nodes. If you actually had a mutation happening, an honest-to-God mutation where you lose the original state, right, you will actually modify F, you will follow down the path here, modify F, link E, and you will not need to do this creation along the way to be able to preserve the original state, right? So there's a trade-off here. Nothing is for free, right? The trade-off is that we can keep the original state, and if we needed that, because that's the base table and we cannot modify it, that's great, right? The cost is that we do need to do this additional copy here, right? The index implementation today uses some idea similar to this. It's not exactly this. We actually do not do the copying along the ways. We do some kind of reference counting in the nodes here in the lower parts. So I'm going to go back to the presentation now, and I'm going to essentially give you kind of like a brief of what follows, but I don't think we have more time at this point. So I'm not going to talk much. I'm just going to give you the ideas of what is here, okay? So in the slides that follow, we have a description of the actual classes that are used for implementing index and what they do. So if you were going to go to the GitHub code, you can use this as a way to, like, navigate the code and understand how the different classes are used. One of the core ideas that I didn't mention before is that since we need to represent indices of different nature, like just a few values for which an array is great, or even a single range for that example with the whole table, right, from 0 to 999,999, right? We literally have a class for representing single ranges, and then we have another class for representing small indices of just a few hundred values or a few thousand values, actually. And then we have the actual, main dish implementation of the big indices, which is the most complicated one, really. These other two are relatively simpler, should be easier to follow. The idea here is essentially from object-oriented programming is like, having one interface, all these classes have the same operations implemented, and then many implementations. The complicated part about that, though, is that you need the Cartesian product in terms of operations, right? Because a single range needs to know how to operate against another single range, a small index, and a big index, and the same is true of the other two. So that's pretty much it. The classes that implement this beast are called here index. You can see the path here. This is the class. And index essentially is the full API. And we have one class called read-only index. It's not a great name, but the intention of this class is that it's a base interface. It's a base interface that only has the read operations. It has no mutations. So if you have a function that only needs to read data from an index, it doesn't need to create new indices by doing updates or results of set intersections and things like that on top of the index. You can use this in the signature of a method to signal that you don't plan to use the other operations, which may give you some efficiency as the result. And with that, I think I should go into either questions or letting you guys go to have your lunch before the next meeting.
Okay, so I have one question. So, for this group and what we're doing, index is mostly invisible to us, and it just magically works. At what points does it become not invisible, where it's something that we need to think about?
Most of the times I talk about index with people on the customer side of Deephaven Enterprise, and I'm going to guess it's going to be similar for you guys. It has to do with two potential things, okay? The first thing is we're talking about how to make some query go faster. You have a query, it has lots of data, you're executing the query, it's taking longer than you actually would prefer. You want to understand how to make the query go faster. Sometimes, not always, sometimes that ends up in a conversation about what things are faster in terms of index operation. Okay.
What? Oh, sorry.
And second,
Sorry.
no worries. And
We
second,
recorded it. We're good.
the second one, and I apologize in advance because this is typically my fault, it's a bug. Index shows up as either an operation that throws an exception, or given that it's a pretty complicated data structure, sometimes we make mistakes in software, big surprise. And this is kind of horrible. The wrong data shows up in your query, right? So if the wrong data shows up in your query, like you're positive, this is not supposed to be there, this row cannot possibly be part of the output, there are two possible sources for that, right? One is the implementation of the particular operation that you are executing has a bug. Let's say you're running a join and the logic for join has some, thingy that doesn't work. Or join is doing something with an index, most commonly actually, to be honest, and the index itself has a bug, right? There are some corner cases in index because of all these different representations And we run into corner cases every so often, and there has been a process where typically we make a change in index, and for a few months we see some of these and then fade out, and we see less and less, and we don't see any until 5 months later, because it's like a very rare case. But yeah, those two come to mind.
Christian, I have one follow-up question actually. So
Yes,
you
sir.
said the index has one interface but multiple implementations.
Yep.
So first question is how the system decides which implementation to use for which particular table or
Yeah.
use case.
Yeah,
And second one is can a user decide which implementation? If the, like you said, if for some reason that query just ran slow and the system couldn't figure out the best way, the best implementation to use, can the user specify a particular implementation, say force it to use it?
I hear you. I'm going to answer in the opposite order, okay?
Sure.
The user cannot specify the implementation. The ways index becomes visible from APIs is in things like, if you get a barrage message, the message itself may have the rows, right? Like 1, 7, 25, and that naturally gets represented as an index, right? So if you, I'm imagining things here because I haven't actually seen this interface, okay? But I'm imagining if you're in the low-level code that handles a barrage message, you will see one of those, right? At the level where you are typing a query, or at the level where you are writing code for the client API, I would not expect you to actually be handling indices yourself, and there's no way for you in the APIs to essentially tickle the implementation of an operation like join and say use a small index here. There's no way. Okay. For your first question, okay. Not always, but many times, the way an index is created when an operation is bootstrapped, okay? And when I say bootstrap, we need to think about this. I understand that you guys already had the talk about how the LTM works and ticking tables essentially are implemented, right? Based on LTM cycles and update cycles and things like that, right? Indices are involved in how the update cycle works. You have ways to essentially ensure that an index only applies for one part of an update cycle. If another update cycle starts, index is smart enough to know that it has a second part in the second update cycle. So that's another world of index complexity. But that was a side track. Going back to your question, when a ticking operation is bootstrapped, meaning not on the 7th update, but when the query is first bootstrapping the first update, right? When that happens, the data structure that is used to create the initial index looks like a builder pattern. You may have seen the builder patterns in many programming languages, and the builder pattern essentially for index looks like add 1, add 7, add 24, add 49, add the range for 100 to 300. Most of the time, if we are lucky, we're doing this actually in sequence, which helps us a lot with how we manage the memory and how we create this initial index, right? So this builder, when the query bootstrapping tells it, okay, this is it, give me the actual index, I have no more values for you, at that point makes a decision based on the actual data that it got and puts that in the right type of index, and from then on, that index is used. One. Second, the smaller versions, which are very important to be created first, right, if you have just a few values, the smaller versions cannot hold more values if you keep adding to them. Very obviously, in particular, if you have a representation that can only hold a single range, if you have 0 to 1000, right, and you now want to add 2000 to it, that implementation doesn't have anywhere to put that. So it needs to turn itself into the next implementation that can hold a few thousand values, create an array, put the original 0 to 1000, and then add the 2000 there and give you that back as a result. Okay? So those are the two ways in which indices, one, are created, and two, adaptively move from one to the other. One thing that does not happen today, very commonly, it only happens in a few cases, is going in the other direction. Thankfully, we don't have many operations that actually make an index be reduced
Smaller.
for the big one, right? But a potential pitfall for us is that if you are able to write a query that should shrink an index over time, right, you may not necessarily see us reducing the memory utilization to the point that you could imagine it will go. Now, the saving grace for that is that it doesn't really matter that much because the implementation for big indices is not memory inefficient in the sense that it will waste a lot of memory for those values. The thing is that it's not as efficient as, imagine the case for a group result, right? Let's say that you have a table with 1 million rows, and each one of those 1 million rows is a group by result with 3 or 4 values. Those 3 or 4 values need to be really packed as tight as you can because you have 1 million rows, right? In that case, if you have the index representation that is capable of storing a lot of values there, we have a memory problem. In the cases where you have an index for a whole table, which used to be big, go to small, that's one table. It's not a row in a table, so it's not that relevant.
I have 3 things. One, I want to apologize for yelling in all your ears. My sort of my daughter's fault on that one. I thought I was on mute. 2, and then 2 and 3 are questions. And to be fair, I floated in and out a couple of times for other work, so you might have answered them. But in regards, I mean, the way I think of indexes, as you described them, is mostly I don't have to care about them in my role. But the way I might care about them are 2 things. Either, and these are sort of the questions. A, is there anything we should be bragging about other than, hey, indexes are important and we did some good work and it's hard and we're smart, yay us? If that's all we're going to say, then probably I won't ever say it. But is there anything specific we would brag about? And then 2, I know it, and you might have mentioned this, I might have missed it, but whatever. I know that you have at different times, you or Charles have casually just said things like, you know, in reference to roaring bitmaps, and like, oh, this is kind of cutting edge and new, and we use it, and it's, you know, and then oftentimes when that's been said in a meeting I'm in, the person on the other side seems to make a face like, good stuff. Can you just react to those 2 things from a, you know, sort of company messaging point of view?
Yeah. So I think the 2 answers actually conflict to one. From the point of view of bragging and roaring bitmaps. Okay, so to give a little bit of idea of what roaring bitmaps are. Roaring bitmaps is a data structure that is relatively new in terms of design and having a paper being accepted in a conference, right? Because if you look at the world of data structures in computer science, it's a pretty old world, right? We're talking about dinosaurs here, right? I mean, binary search trees, ABL trees, red-black trees, how to represent lists. These are things that were discovered literally in the 60s and 70s, right? So publishing a paper here for some like new fancy data structure typically gets very esoteric for use cases that, you know, I mean, nobody cares about except 2 folks in one corner of the world, right? But then things like MapReduce came, right? And with MapReduce, you have, and you know, big data systems or whatever, you have hundreds of billions of gazillions of rows, and people care about how to do these operations efficiently. And roaring bitmaps is, I mean, if you look at it, it's one of those things that you say, that's clever, but it's not an idea that you will say, oh, I mean, I need, like, you know, advanced calculus, different partial differential equations to understand what this is. And the idea behind roaring bitmaps is that if you have values that are tightly packed together, like, you know, 1, 3, 7, 9, we're going to use an actual bitmap to represent this, like, you know, 0s and 1s in memory, like tightly packed. And, you know, if there is a 1, that value is there. If there is a 0, the value is not. That is not a very efficient representation if you have, you know, just 2 values in the range to 0 to 1 million, because you need a lot of zeros in between. But then for parts of the space that actually do have just a few values, we're actually going to have an array. And the way that we're going to do this is that we're going to partition the space in fixed size slots of 2 to the 16, 65K values. and depending on how tightly packed in that particular piece of the space of possible integers we're going to use a representation of a bitmap, often an array, or sometimes use another more, a smart implementation there, like run length encoding, which has some kind of like very simple compression. Anyway, this was like, all the rage for things like MapReduce. And if you actually look at the implementation of MapReduce in GitHub or whatever for Hadoop, it uses this. And once something started using it, everything started using it because it saved a lot of memory. We are using some parts of the implementation and the idea, and we are combining that with some ideas of our own from what we had before we made the change. That change is relatively recent in Deephaven. Is recent in terms of internal engine data structure. This is from the last 2 years. The original index implementation is at the beginning of the story in Walleye many years ago, and then there was an intermediate implementation that we did that had some of these structural sharing ideas that I mentioned before. The first implementation was purely functional data structures, and it had the problems that Chip was referring to with his question. So anyway, to go to the first part of the answer, right? I honestly believe, and hopefully you don't see me doing this very often. I don't think I do it. I'm not very, the bragging part. I believe we have the best freaking implementation for a data structure like this that there is, period. I also believe that if somebody took the index implementation that we had and put it into Hadoop or MapReduce, those guys will be happy. I think our implementation is better. I don't think it's.
So let me ask you a question.
Yeah.
Could I say something like that publicly? And if they did it, we would actually be happy, or would we be? I mean, there's no reason to think that that would be competitive. I mean, it is competitive, of course, but not really directly competitive. And in the spirit of openness, it's great to say something like that.
I understand, and from my background and my view of the world, my answer to that will be this, right? I have no problem saying that in a context like this with you guys here because we're close. If I were to say that in a more public or to people that I don't know directly context, I need to back up what I'm saying with, facts and actual data. And people typically do that in two ways. They either publish a paper. I could try to write a paper that could actually be fun. I've done that in the past, and it could be some amount of work that I'm more than willing to do. Or we could write something a little bit more talking to the world in terms of a white paper in a website, right?
Yeah, but I'm relieved from that. So if a conversation happens to go in the direction of indexes, I could make a comment like that. I could say I wouldn't have to say we think it's the best. We could say we're very proud of it. We even think that if something like if the MapReduce people were to look under the covers in our open source and see our implementation of these indexes, they might find something that's pretty interesting and pretty additive to what they do. And a sentence like that, we're not really measuring our anatomy there versus theirs, but 1 in a million people hear that and go, "What? Whoa, okay, let's see if this guy's got chops," right?
Yeah. And to the extent that we can have presentations like the one here and more supporting data for which we already have some, right? I mean, we have some documents written, we have some presentation slides. We can very quickly give people soft type references, not heavyweight a paper in a scientific journal kind of reference, but soft type references to back up what we're saying. I totally agree. I think we can do that.
Good, thanks. I'm done, and I won't yell at you guys in your ears anymore.
It's okay. I want to leave you guys to have some time between now and your next meeting. So